All right, this will probably be the last video here for 6.5. Just one last thing to talk about. And I think this one's pretty cool. This is about the force that a fluid puts on a vertical object suspended in liquid. So here you see we have a dam stopping water. And the reason that dams are built in such a way that they are thicker on the bottom than they are on the top is all about the pressure. The deeper that you go in liquid, the more pressure is put on objects. So there's a nice equation to it, the pressure depth equation. The amount of pressure is just the density of the liquid, this W, times the depth that you are in the liquid, H. So you can see here that if you have water or something, the deeper you are in the water, the more pressure is being applied, and it only has to do with depth. Moving to the next page here. What makes that really cool is that you can figure out how much force is being applied on a horizontal object. So all it is just the pressure times the surface area of the container, the bottom of the container. What's really neat about that is that it doesn't actually matter how much water you have. It's all about the depth. These two containers, even though there is more water in the first one than there is in the second one, they are still feeling the same force on the bottom of that container because they are at the same height. So even, like, it doesn't matter how much liquid there is, it all is about the depth that you are in the liquid as far as the forces go. They have a little calculation here, which I think is fascinating. Again, just to show you how heavy liquid is. If you have a pool, it's a rectangle, it's 10 feet by 20 feet, so it is a very big, wide pool, and it's 3 feet deep. Only 3 feet deep, you have 37,440 pounds of force being applied to the bottom of that pool. Okay, to move on, what we're going to do, because this is easy stuff where you're just multiplying the three numbers together, the density of the liquid, the depth of the liquid, and then the surface area of the bottom, instead of having a horizontal object in the liquid, what happens if you have something suspended vertically in the liquid? To do something suspended vertically in the liquid, the force is going to change the further down the liquid that you go. So instead of just having a constant force on the object, we're going to have a variable force because the object is at different depths. So we're going to take our object, we're going to, again, slice it into these horizontal slices, figure out what the force is of each individual slice, and then integrate over all of that. This one they have simplified down to a pretty easy equation. So you'll just have this equation in front of you when you answer these questions. This equation is whenever you have an object suspended vertically in liquid. It's the density of the liquid times the depth of each of the individual strips times the length of each of the individual strips, dy. And then we have our example here. So we're going to do this example together. A flat isosceles right triangular plate with base 6 and height 3 is submerged vertically, base up, 2 feet below the surface of a swimming pool. Find the force exerted by the water against one side of the plate. Okay, so just to go over to one note here, we have the base of 6 and a height of 3, and it's 2 feet underwater. Also remember it said it was base up. So we have our base. Triangle looks something like this, right? So this distance is 6, and then the height is 3. The liquid is 2 feet above the base here. For these questions, it honestly does not matter where you put your origin for your X and Y axis, although sometimes it'll be easier than others. You could put the origin so that it's up here at the top of the water. You could put the origin so that it's at the bottom of the triangle, or you could put the origin up here at kind of the top of the triangle. It really doesn't matter, but for me, I think I'm going to put the origin here at the bottom of the triangle. That way we're always working up. Okay, so again, you're going to have to slice your object. So here we have a horizontal slice of my triangle. This slice is located at a value y. Remember that for the triangle, we know what the base and the height is, which means that we can find some points. If this total length is 6, Then half of the length here as I move up the x-axis is 3. So I'm 3 units horizontally. Also remember the height of the triangle was 3, so I'm 3 units vertically. The reason I put that point there is because we do need to know the equation of this diagonal line. If it's at 0, 0 and it goes to the point 3, 3, that means this line has to be the equation y equals x. Just the line with the slope of 1. I promise that's an x there, not a little y. I just can't. I can't with this thing. Okay, great. So from the formula, and I'm just going to write the formula down over here. Remember that the total force that's being applied on the side of this object was the integral from A to B, the density of the liquid, the depth of each of the strips, times the length of each of the strips as a function of y dy. So we need to find the depth here and the length. We'll do the depth first. If my triangle is 3 feet tall and it's 2 feet underwater, that means that the top of the water is located at 5. Which means that if my strip is here at y, then the depth is this distance from the strip to the top of the liquid, so we are at depth 5 minus y for any given y value. We also need to find the length of each of my strips. So the length of the strip is going to be the total horizontal distance of the strip. You just have to be a little bit careful here. This is where we needed this equation. If we know that the height of the strip is at y, and the equation for the diagonal line is y equals x, then if I am at height y, this horizontal distance is x. But that's only half of my line. To find the total length of the line, I'm just going to double that, so we have a total length of 2y. Great. And then just plugging that into the formula here. So we're going to be integrating, we need the limit. Sorry, going back to the picture. The limits are going to be where all of your slices exist. Our slices exist from 0 up to the top of the triangle 3. So we're integrating from 0 to 3. The density of, I think you said it was water, right? Blah, 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 is vertically suspended. Oh, it says a swimming pool. All right, so we're just going to, water. For whatever reason, this book doesn't like to give the density of water. In the question, it just assumes that you know it. So the density of water is the 62.4. So that's going to be the W, 62.4, times the depth of the strip, which remember we found up here. The depth of the strip is 5 minus y, times the length of the strip, which remember was 2y dy. Okay, we can pull that 62.4 out of the integral just because it's kind of obnoxious and in the way. Distributing the 2y into the parentheses here, we get 10y minus 2y squared. 62.4 stays. We're going to do the antiderivative here. 10y goes to 5y squared. Minus 2y squared goes to 2/3 y cubed. And then we're evaluating this between 0 and 5. So we're going to plug the 5 into that. And we don't need to worry about plugging the 0 into that. So we still have the 62.4 out in front. Plugging 5 into this one is going to be 125. Minus, I need a calculator for this next one. Minus, plugging 5 into this one, we get 250 thirds. So all of this together is actually a really nice number, 2,600. And remember, this was force, and we were in pounds per cubic foot, so this is just going to be pounds. Just to double check, going back to the book, make sure we got the right answer here. Oh no, I goofed it. Where did I go wrong? It must have been in the last little bit here. Let me double check. I guess the answer wasn't so nice. What did I do wrong? 5y squared minus 2/3 y cubed. Did I plug something into the calculator wrong? Probably. That part was right. That part was right. Oh no. Let me pause it and I'll figure out where I made a mistake. Oh, I know where I made a mistake. I don't know why I wrote a 5 here. So instead of integrating from 0 to 3, I for whatever reason started writing 5s instead of 3s. But those should have been 3s. I should have been plugging 3 into this stuff and not plugging 5 into this stuff. So this was all wrong. All right, if you plug 3 into it, I promise you that you'll get this number here, which was the right answer. So oops, that was my bad. But there we go. So that's how you do the question. Just to break it down again, here's the formula for an object suspended vertically in water. You want to take the density of the liquid times, you have to find the depth of each of the strips as a function of y, where your strip is located at y, times the length of your strip as a function of y, and then you just integrate over that, where your strips exist. But pretty cool, right? So just suspending a triangle between 5 and 3 feet underwater, it's 1,684.8 pounds of force that you are feeling on the side of that object. So that's why if you've ever been in a pretty deep pool and you dive down to within, like 5 to 6 feet underground, it starts to feel really heavy. Your ears start to hurt. Your eyes, if you try to open them, would start to hurt. And that's because the side of your body is feeling about 1,600 pounds of force on all sides of your body, the top, the left and the right, and below. So there's a lot of force that's being applied to you the further that you go underwater. Okay, cool. But that's it for section 5.